Thank you also for the invite to give this talk at this nice workshop that I have enjoyed this week. This is going to be a summary of collider challenges for QCD, as Jennifer said, from a theory perspective. I was asked to do this or to give the talk in a broad way and a non-technical way. So that's what I'll aim to do today, is to give a flavour of the ideas and challenges which remain for us as we look forward. So looking ahead then, I thought it was a good place to start. As we look to the future, it's good to know where you are just now. And so I had to begin this slide with the Large Hadron Collider itself. It's particularly appropriate because I discovered just this morning that 13 years ago today, the 10th of September, was the very first day that protons circulated in the LHC. And since then, we've come a very long way and learned a lot. And it's particularly appropriate it's here because we have so much more to learn from the LHC, and we will learn in the next 15 years or so. Of course, we also have current other experiments like Bell 2 and the muon G-2 experiment. Then looking forward in the medium term, shortish term, the EIC is confirmed. We're not quite sure exactly which or when colliders will come after that, but we are fairly confident, at least the European strategy tells us, that we will have some kind of E plus E minus Higgs factory and some future high center of mass circular collider. So these and all the others whose pictures are not on this slide gives us access to many different aspects of QCD. They all have different strengths and allow us to probe different physics, which is very exciting as a particle physicist. But at the same time, we still have the one theory of QCD. So we're looking at our SU3 theory of color, but in many different regimes and many different aspects of that same theory. So I was asked to talk about challenges. And thinking about that, I think these challenges fall into two broad categories. So the first is, can it actually pass all these tests? And that lends slightly to some discussion we had earlier, that actually is our understanding of QCD, or SU3 gauge theory, is that really the color structure once and for all? Personally, I think it probably is, although I wouldn't rule out strong dynamics in other sectors. I think it probably can pass all these tests, as a personal opinion, but we must test it. And that's why we are physicists, that we must explore as far as we can. The second type of challenge that we'll face is, are we actually able to calculate well enough, by which I mean really to high enough precision, to be able to see and extract all the information that's there in the data? Of course, it's a slightly ill-posed question, you know, what is well enough? But I would say the current position that we're in with the LHC, we're not really passing that in the sense that there are many analyses where theory uncertainties are dominant and are preventing us actually making a final conclusion. But that's a challenge we need to respond to, and one that we need to keep a very close eye on as we look to the future generations of colliders. So I said that I thought that probably our QCD as a theory of color will remain unchallenged. That doesn't really apply to the whole of the standard model as the be all and end all. And we heard in Yuri's very nice talk just this afternoon about a few persistent possible signs of new physics, which have been around for a while and are not going away, and are in fact increasing in their significance. So RK is one example of that. I just picked one flavor anomaly. Of course, we've just heard about many more. And also the anomalous magnetic moment of the muon, where with the excellent new Fermilab result, backing up the old Brookhaven result, our standard model prediction remains stubbornly far away. And both of these actually already hint at there being a greater difference between electrons and muons than we have in the standard model. There, the idea of lepton flavor universality is present and has been unchallenged until now. But they also contain difficult QCD calculations, and in particular require very good understanding in different contexts of hadronic contributions, and are pushing us to improve our accuracy in those calculations, as we have heard about in our other talks this week. So we'll have to wait and see how those develop in the next few years. Maybe they will become our guiding lights towards new physics, or maybe we'll understand some theoretical issue that's been overlooked, or experimental one. What we do have plenty of, though, are many new particles. And when I was making this slide and looking for, actually I was going to make a slide about the TC here, and I was stunned to stumble upon this plot. Actually, I hadn't realized quite how many new hadrons we have discovered at the LHC. 62 to date. At least I think this is fairly up to date in that it's got the new August discovery of the TCC+, which is notable as the first tetraquark with 2 charm quarks, the first doubly charmed tetraquark. But there does remain an issue for understanding within QCD of this and of some of the other states as to actually the dynamics within it. Is it a meson-meson molecule like this picture here, or is it more of a tightly bound state? And our experiments will need to wait and tell us that in the years to come. So we saw a lot this morning about the strong coupling. I just have this one slide here, but I thought it was important when we're discussing challenges for QCD to start with its most basic parameter, its coupling. It's also nice to include because it's always nice to have the opportunity to show a plot like this one on the right hand side, which illustrates, at least for me, part of the real beauty of particle physics, that you can take this huge range of experiments and contexts and energy scales. You can measure the same parameter in each case. You can see that you don't get the same value, but actually we have perfect understanding of why that is, and we predict how those values should be related, and what we see is them all lining up very, very nicely and consistently with each other. Also from the last year's PDG review, the same information displayed in a slightly different way on the left-hand side, where it's organized into the different categories of extraction for the coupling. For example, we have this large section in the middle, the E plus E minus jets and shapes. And one thing I wanted to highlight there was that some of these calculations are actually the latest state-of-the-art theoretical techniques applied to older data, in this case, Hera data. And when we have those state-of-the-art techniques to apply to new E plus E minus data in the future, we can expect much greater precision still, as we heard this morning. And of all the error bands on this plot, the one with the smallest one is the completely separate lattice calculation, which is just the one with the lowest band at the moment, and again offers complementary information and confidence in our understanding of QCD. And when we go to future colliders, we can hope to see that precision increase. Of course, the coupling is central to our ability to do most QCD studies at the LHC, as it enters in so many places. So to follow on from the coupling itself, I thought the next obvious place to go was to talk about perturbative expansions. And here I'm particularly looking at perturbative expansions of high scale hard matrix elements. So this is possible, of course, because of the running that means that as these high scales, the value of alpha S is small enough that you can do an expansion. For completeness here, I've also expanded in the weak coupling. There are some of these terms where the coefficients have primes, and we're understanding more and more the importance of including these electroweak calculations. But for the purpose of this talk, I will mostly be talking about the fixed order accuracy in alpha S. So the unprimed coefficients, these terms in this expansion. So a big change from previous experiments, and even from the start of the LHC, I would say, is that the new standard for LHC calculations is next to leading order. It's very rare to see analyses with at leading order accuracy, true for both standard model and BSM processes, and true for really quite complex final states. And that's certainly been a revolution in, say, the last 15 years, which I didn't expect to be as complete as it is looking from back then. There were three big things that were really necessary before that was possible. The first was the unitarity revolution, which showed us how to more efficiently calculate the one-loop matrix elements that go into these calculations. The second was automation of subtraction to organize the calculation and the cancellations of the divergence. And then there was the development of two alternative methods to consistently combine at that fixed order accuracy with parton showers in MCNLO and POWHEG. And now we have these four general purpose tools shown on the right-hand side here, plus others for specialized processes. And here, the benefit of these tools is in the input file, you can separate, you can state your process and your required, whether you want NLO, whether you want to add showering, and have your fully exclusive distributions out the other end. So if that's the sort of baseline standard for most of our analyses at the LHC, at the opposite end, we have the real state of the art. And at fixed order, that's n cubed LO. And this glue to Higgs result is now 6 years old, but was truly remarkable at that time in terms of what you could calculate with the technology that we had. And I think it's worth just showing the plot from here again of the importance of that calculation to give real confidence that the perturbative expansion was converging. So the green line was leading order, and there's a jump to NLO, which is understood because there's new channels which open at next to leading order. And then as you go to next to leading order in blue and n cubed LO in red, then you see the bands narrowing each time and converging very nicely. Now a lot of time has passed since then in calculational terms. So we now have the full calculation. There were some approximations in that first result. We also have VBF Higgs, BB bar to Higgs, and Drell-Yan results recently. So still an impressive range of processes, but you'll note these all have color singlets in their final state, which removes at least some of the complexity. But there we can expect much more development there. But if these are the two bookends of fixed order expansions, your NLO and your n cubed LO, where the vast, huge amount of work in terms of results in the field at the moment sits at NLO. And we have specialized calculations for many, many processes now, too many for me to give you a list like for n cubed LO. However, we're not yet at the stage where you could consider this a solved process, and each one of those processes takes specialized organization and calculation. One step of recent progress in last year was that we had NLO calculations for TT bar for the first time. So now introducing color charge in the final state for these heavy quarks. And I've chosen just a couple of plots from those two studies here. The first one, again, showing the very nice convergence in the sense that the error bands are smaller from NLO to NLO and in agreement, and more importantly still in agreement with the data points which they are compared to. And of course, this is just one plot, but across a range of distributions, that was broadly the case apart from a few bins here and there. And in this calculation on the right-hand side, the accuracy was also extended to include the decay. And we again see extremely good convergence, very good convergence and agreement with the data points. But these plots also show exactly why it was required and why there has been such a focus on calculating at this level, because these black points do have experimental error bands on them. They're just so small that on almost most of the points you can hardly see them, and it required NNLO before the theory uncertainty was actually competitive with those experimental bands. And that's a theme that we're going to see again and again during the examples in my talk today, that the sheer high level of precision from the experimental data is requiring more and more sophistication from the theory community. Final states with light jets in them are more difficult in terms of NNLO complexity. There are a collection of results available there, and very recently over the summer we had the first NNLO calculation of PP to 3 jets, which is another big step forward as we look at high multiplicity states we're going to have to deal with at the LHC. But it doesn't just stop at NNLO. Actually, before that, I wanted to just describe where the development will come from and how we're going to get from our current approach with these processes to general purpose tools like we have for NLO. And there are two key fronts where there's been very fast development recently. There's a collection of papers from this year, for example, with new analytic results at 2 loops for the processes listed here. And one thing that I have certainly noticed as a spectator to this field is that in the last year or so, there's now become a much greater emphasis on numerical stability and efficiency. Before that, the celebration was in getting the result, which is a massive achievement in itself. But now there is a focus on not just having a result, but a usable result that can be implemented to give you numerically stable results and predictions that can be compared to the data eventually that we get from colliders. Of course, before those amplitudes are useful, you need to be able to combine them with the other parts of the NNLO calculation. That requires the cancellation of divergences from 3 broad classes, the 2 loop, 1 loop with an extra emission, and tree level with 2 extra emissions, each of which is separately divergent, but which will combine when done correctly to give some finite value n. Now, at the moment, there are quite a number of competing approaches for how one is going to organize that calculation. These have all been used in different contexts, and it remains to be seen actually which one of these will allow us to generalize and automate to make NNLO available far more widely. As I sort of slightly prefixed before, the ultimate goal though is not to stop at NNLO. We're well accustomed to having to supplement fixed order calculations with partron shower corrections. That's very mature technology, and the arguments remain the same. You know that if you have emissions, soft and collinear emissions, then the probability of that is enhanced, and therefore you need to sum these to all orders and to evolve in scale from your hard scattering matrix element right down to the shower and hadronization to the observed hadrons that you'll see in your detector. There has correspondingly therefore been a huge development in methods to match consistently NNLO calculations with the partron shower. The 3 main ones are listed here: MinLops, Geneva, and UnLops. And these are all becoming increasingly sophisticated. Again, I've picked just a couple of examples from this year to show some recent examples. This is a Geneva calculation of PP to Z at NNLO, which also combined QT resummation taken from Radish at n cubed leading log. And then the shower it was linked to was Pythia 8 for both shower and hadronization corrections. And you see in this region the very good agreement. In this band above 30 GeV, you actually begin to expect to need the N and LO calculation with another emission, although it remains within the uncertainty bands. Those uncertainty bands increase in size. And again, the very small data errors show you why there is such a rush to get this accuracy. I also wanted to highlight in February the first time that N and LO plus parton shower was produced for a process with color charged particles in the final state. This was for TT bar, and the full thing is the blue min-low PS result shown across here in this distribution, and broadly compatible with N and LO, showing that method has kept that accuracy, and again in good agreement with the data. So talking about matching these calculations to parton shower is a good opportunity to talk about event generators in general. And I was very aware when I was talking about how far we could get and couldn't get in calculations that it's important to stop and comment actually about what a success story event generators are in terms of collider physics in general. They're central to almost all of the physics analyses which go on, both for signal and background processes, and do that extremely well. I thought I needed to find a plot. I was looking for a plot to try and illustrate this, and I started looking randomly at analyses, starting with the most recent ones. This is a September one. And the first paper I looked up, I had all of these different channels. So just for completeness, this is a study of Z gamma jet, but where the Z decays to neutrinos, so missing energy, plus photon jet, in various different control and signal regions, and all with different processes which dominate and need to be taken into account. And from the same paper, the full list of those processes. And you see from all of these different columns how involved it is and what high accuracy is actually available. So lots of different generators for different processes depending on where you can get the higher accuracy. These ones which mention MEPS at NLO, for example, have an NLO calculation supplemented and merged correctly with higher multiplicity leading order matrix elements. And then, of course, we have the issues of PDF accuracy, the choice of parton shower, and the tune of that shower, all going into plots like these, which you find all over the place, of very excellent agreement and understanding in different kinematic regions. However, the story is not complete or finished with event generators either. In many cases, Monte Carlo uncertainties can be very substantial and can be a big part of the error budget of experimental analysis. And one part of that is it's actually even quite difficult to define what they are. You can sometimes change parameters within the tools. More often they're estimated as the differences between tools, and trying to pin down and understand these as the experimental precision gets higher and higher is a priority in many different regions. There's often analyses also where you see that even in a process which is quite well understood, like this was Z plus jets, that large correction factors are required. And this is just an example where in order to match control region data, then Monte Carlo simulation was multiplied by factors varying between 1.1 and down here to 0.5, 0.4, something like that. And so large correction factors there indicate that there is something in the modeling which can be improved and should be improved. There is a large event generator community, though, working on many different aspects. To highlight some of the high priority parts at the moment, merging and matching with higher order fixed order is a big topic. I mentioned the N and LO plus PS. There's now the first attempt of N cubed LO plus parton shower. Given the availability of fixed order matrix elements, that's a relatively low or relatively specialized corner at the moment, but can easily become in the future more important. But merging different multiplicities of NNLO and NLO and eventually LO is very important to deal with our data samples. There's also a big effort in understanding what is the accuracy of our showers, for example. They're often quoted as leading logarithmic accurate, but to consistently define what that means and what it means to be next to leading log accurate is non-trivial because of the complexity of the final state and how much goes into it. And then, of course, if you do agree on a definition, you need to agree how, then work out how to increase it. And this plot here is an example of the new pan-scale showers, where one can track the logarithmic accuracy very well. There's also Dyer and Deductor and some other recent developments where the underlying accuracy is being really focused on. And lastly, I wanted to mention the importance of improving the color description to subleading color to make sure we're understanding and tracking the color evolution within processes, which is seen as emissions. And all of this has to take place with a very close eye kept on the computational requirements. It's great that we have these multi-purpose tools that can do NLOPS, for example, for most processes that you want, but the actual CPU days and weeks required to make large enough samples that can give you high enough statistics for all corners of phase space probed in your analysis is highly non-trivial already for run 2 data at the LHC. So there's a big effort into how this can be tamed and controlled and improved, looking at issues of negative weights, for example, already with a focus to the high Lumi LHC, but also looking much further into the future for SCC. It's very important that we're not only able to construct these tools, but able to tune them and make them efficient enough that we can use them widely with the computational resources that we have. Having spent a while then talking about partron showers, it's a sort of sidestep into talking about resummation more generally. They represent a perfect example where you can't just stop at fixed order and think and find that sufficient to compare with the data that you have. We had a talk about resummation by Daniel de Florian earlier in the week. The general kind of theory rule of thumb is that whenever you have multiple scales in your problem, whenever you then go to integrate, whether as a loop or as a phase space integral, generically that will lead you to logs of ratios of those scales. And in principle, those are fine if your scales are all of the same order. If you have scales that are very disparate, that span some large hierarchy, then those logs will lead you into trouble. And by trouble, what I mean is that your nice fixed order expansion is not going to converge the way that you would hope and expect. This has been seen in many cases for a while. For example, returning to our glue to Higgs example, even if I think of it without all the complexity of loops and extra emissions, then you have 2 scales of possible transverse momentum and the mass of the Higgs boson. And it has been calculated and required to be calculated to next to leading log, for example. Another reasonably recent plot just illustrating how or the gain that you can get from increasing the accuracy of your resummation is this example for PP to Z, where the fixed order and logarithmic accuracy are increased together. So the green band is your sort of, you start with next to leading log in PT and leading order at fixed order, and then you end up in the red band at n cubed leading log in PT resummation and NNLO fixed order accuracy, which has massively shrunk the band. And again, you see and are confident in the convergence of this. From this one plot, you can't entirely see, but the impact of the resummation is all largely in this low region. So that's a couple of examples of resummation being important, but that was examples where you had to deal with two scales. So whether it's PT and MH or PT and MZ, then largely your processes are characterized like that. When you go to looking at multi-jet events, your problems become much, much worse. So this is an example, admittedly quite an exceptional example from 2015. It's the CMS experiment, where in one collision traced back to a single vertex, they have 12 jets with transverse momentum above 50 GeV. So I'm talking about high multiplicity or high numbers of colored particles, but I'm not talking about that in the context of MPI or underlying event. Here I'm really talking about hard scale perturbative extra colored emissions, either quarks or gluons. And an event like this comes with a huge number of scales. Each one of these 12 jets will have its own PT. Many will be close to 50, but not all. Then for any pair or subset of those jets, you can make an invariant out of them, which will give you another scale in the problem. And then, of course, there's the total partonic center of mass energy, which is not the full 13 TeV, but in this case, from memory, I think was maybe 5 or 6 TeV. So you have a lot of scales scanning a big numerical range, which means that you have a lot of logs, which can and will damage the convergence of your perturbative expansion. We understand the calculations well enough to know that you get these logs arising at every order in alpha S. If your alpha S is about 0.1 and these ratios are of any sort of reasonable size, then suddenly the expansion is not converging as quickly as you would like. So it's a very complicated resummation regime, but luckily for us, the matrix elements simplify in the limit where these logs become large. So we call that the high energy limit, and it's where the pairwise invariant of any two particles become large and the transverse momentum is finite, much like they simplify if you take the limit of transverse momentum to 0 in an amplitude. Here it's just a bit more involved because there's more particles. And exploiting this simplicity then, we've shown within the high energy jets framework that you can sum up all these log terms, the leading log terms, where you get a log for every power of alpha S, in a flexible event generator. So you still have, it's still Monte Carlo, you still have access to the 4 momenta of everything produced, and so you can apply any experimental cuts that you want and are not reliant on, say, inclusive results. There are particular cases where these logs are particularly important. One example of that is in Higgs plus dijet production, and that's because if you're looking at vector boson fusion production of a Higgs, in order to suppress the background, then typically VBF cuts are applied which require large invariant mass between the jets. Now that's very sensible experimentally because it does a very effective job of suppressing the QCD background, but at the same time, it exactly enhances the arguments of these logs which become large. So the plot that I've chosen down here is a Higgs plus dijet plot, which illustrates the impact of the logs, but at the same time illustrates the power of the high energy limit. Not only does it let us calculate the log terms, because of the simplification that you get in the high energy limit, then actually we can calculate our Higgs plus n jet matrix elements with finite top quark and bottom quark mass contributions. Now, at fixed order, that's highly complicated because the leading order is already a loop, and not just a loop, but a massive loop. And in fixed order, the highest multiplicity you can get is Higgs plus 3 jets at leading order with the full mass corrections. But because of the simplification in the high energy limit, what it means is that we can add jets without adding legs to the loops. Basically, each emission in the limit kind of separates from the others. And so instead of having to go to pentagons, hexagons, and so on with Higgs bosons propagating, then with the just triangles and boxes, you can get Higgs plus any number of jets with the finite quark masses in this limit. And that's what's illustrated on the plot, where the difference between black and red is the difference purely of including the full finite quark mass corrections. And out here at the invariant mass of the two jets of 1 TeV, that's already a 50% effect. And when integrated over the region, does have a very noticeable effect. It's compared to the line in blue, which is our best attempt at the fixed order. So it's the finite quark masses at leading order multiplied by NLO K factors evaluated in the effective theory, but bin by bin to keep the kinematic shape. And the difference between the full resummed finite quark mass result and the best fixed order result is a factor of 2, already at 1 TeV. And in fact, when you integrate over the region, what it tells you is the estimate of applying those VBF cuts is that they should be about a factor of 2 more effective at separating or at suppressing this QCD component than you would get from the fixed order estimate on its own. But earlier on, I was saying the LHC standard was NLO, and actually these predictions here have formally leading order accuracy, which is the best we can do in very complex setup with all the different scales. However, there's a lot of ongoing work at the moment to increase our accuracy to next to leading order. And we do have various prescriptions for how to do that. And the first of these we published last year. This is now W plus dijets, and as a function of transverse momentum of the leading jet. And here you firstly can see, when compared to this Atlas data, that the blue leading order plus leading log, sort of most basic resum prediction you could make, clearly is not getting the shape correctly, but nor would you expect it to, because the high energy limit exactly relies on the transverse momentum being all roughly of the same scale. And so there's no concept of evolution in PT in the description. It's also why we have available some matching with Pythia, although it's not shown on these slides. But what we can do is to match that to an NLO calculation. The pure NLO is shown in red here. And what we find is exactly what you would hope, that at large transverse momentum, when you combine the two descriptions, then you end up in between the two and giving a much nicer description of data across the board. And lastly, on the topic of the logs, since we're looking ahead and we're talking about the challenges, I wanted to illustrate why it's so important that we understand these at the LHC in preparation for the future colliders. So this plot here shows invariant mass of the two leading jets in W plus dijets, and the red line is 13 TeV LHC with a 30 GeV jet cut. Now, if you then just increase the center of mass energy, then of course the cross section jumps up enormously, but that's not really reasonable. We're not expecting to keep the same jet cuts. And what can be seen if you study just the jet rates alone is that if you increase your min PT cut to 80 GeV at 100 TeV collider, then cross sections become very similar. You can kind of roughly see the peaks are about the same in this plot, and the ratio of n+1 jets to n jets becomes very similar to 13 TeV at 30 GeV. So the red and the pale blue, if all you do is integrate jet rates, look very similar. But one glance at this plot shows you that they're really not very similar at all. At the LHCs, you can see this very steep drop off from the peak. And that means that out in this region of large invariant mass, where the high energy logs are enhanced, they're enhanced and important in a region where the cross section is many orders of magnitude smaller than the majority of the cross section. So given enough statistics, you can do interesting studies out here, but in general, they're quite a small, or in a small region of phase space. But at 100 TeV collider, that is not the case. Out here at 4 TeV, it's only slightly less than 2 orders of magnitude down from the peak. It's a much slower drop, and if anything, slightly leveling off. And so what that means is when we look forward to these very high center of mass collisions, then you can expect to find that the contribution of these logs at large invariant mass will be much more numerically significant. And even with the logs aside, it's also true for the high multiplicities. We saw when we were making this plot that if you truncated and didn't include the 4-jet and 5-jet components in this dijet sample, then they had a very significant numerical effect on the out here at large PT. And it's the same in the MJJ plots, that out here there's a huge effect from 4-jet, 5-jet and above. And in our prescription, we keep adding until we see convergence. So which we define as where we're not seeing a difference in the plots. And so here this actually included out to 6 jets, for example. So that's the type of considerations we're having to make with hard scattering matrix elements, but those alone will get you nowhere without the PDFs that you need to connect them to the total cross-section in a proton-proton collision. And now that the perturbative accuracy in the matrix element has become so large, the PDF errors in some cases has become very significant. So this is an example just of one process, PP to HBB bar, where the calculation is such that the scale uncertainties are down to just a couple of percent. But the combined alpha S and PDF uncertainties are as large as 10%. So clearly this is now a region where we need significant work to really progress here. Even when you go up to 100 TeV, some of the scale uncertainties have increased a little, but these remain of a similar size. And so are things we need to understand and improve. And our new array of experiments directly designed to probe PDF should hopefully allow us to do that. Even within PDF fits, in the data that go into those fits, the experimental errors are now low enough that often other sources of error have become very significant. So just to give a concrete example of what I mean by that, if we look at the WZPT data from the LHC, which is now included in PDF fits, including this week's NMPDF 4, there are issues which stem from that data because traditionally the only errors which enter those fits are experimental errors. And the experimental errors on those data can be as low as 0.1%, which is very, very tiny compared to the theoretical error on the prediction of that, which is 1%. And of course that matters because if you want to link between PDF and measured data point, to work backwards to the PDF, you always have to go through the bridge of the theory prediction. So it's clear that now theory errors have to be incorporated into PDF fits, but it's actually a very subtle problem, as first pointed out in this paper by Harland, Lang and Thorne, and there's a very recent paper from this year looking at it in the context of NMPDF. Part of the problem, or something that one has to be aware of, is that if you consistently include theory errors, which is very complex across processes if you're using the same PDF at the same factorization scale, once you've sorted that out and you have PDF fits from that, if you make those predictions, new predictions from your new PDFs, then you actually double count the theory error. And to assess that in a consistent way is non-trivial, but if you do, there can be big benefits and it can massively reduce this error under certain circumstances. And I think we will see in the years ahead more understanding and use of approaches like that. Nuclear effects within PDFs are important, and here I'm actually talking about nuclear effects within proton PDFs, where again, until very recently, that error was considered too small to really be significant, but now is. And electroweak effects as well, which I won't discuss too much, just to observe that they're there. But looking into the next, in the sort of time scale of 10 or 15 years, then we have many actually sources of new PDF input, which should really help a lot. One big area of growth has been that it's now possible to calculate PDFs on the lattice, which long ago was possible only for moments, but now actually you can compute quasi-PDFs that are mature enough that you can actually compare with the latest global fits. So this was taken from last year's PDF lattice review. If we look at the unpolarized PDFs up in the top row, then the top 4 here are lattice quasi-PDFs being compared to these 3 just general global fits. And the uncertainty on the lattice PDFs, it's a bit hard to unpick underneath all the different colors, but the uncertainties are larger here, but they are compatible. And the lattice calculations also allow you to look, for example, polarized PDFs and transversity. And there's real opportunities here for the 2 communities to help in different problems. Clearly, the global fits from the DIS data and all the other sources of PDF fitting data are far more sophisticated at the moment, because they have been around and evolving and improving all the time. But that means that in, say, a mid-X region, then those determinations can provide good benchmarks with which to improve the lattice calculations. And here, I think even the lattice calculations admit there are improvements required in terms of dealing with lattice effects. And those benchmarks can help to do that. But where the lattice can help in general determinations is that they're not limited by the X values of their data, for example. So where there's less constraint out at small x or large x gluon, for example, lattice determinations could have an input there to help where there's a shortage of data. And that also holds for nuclear PDFs, transverse momentum dependent PDFs, and GPDs, where lattice calculations can input in all of them, where the standard determinations are not quite so sophisticated yet. But even with those determinations, looking ahead, we have new experimental input from EIC and SMOG2, together with existing experiments which are running at the moment, which is going to increase the range of fitting power. And these are plots just taken from the EIC yellow report. Here for nuclear PDFs, this is gold and this is iron, just showing the effect of including EIC data, the projected effect on reducing the uncertainties in both cases. When talking about PDF results from future colliders, then I thought I had to mention polarized PDFs, which is one of the big goals of the electron ion collider in the States. And one of the big things that should allow us to do is address the question of where does the proton spin come from. So we know that the proton spin is measured to be a half, and that it will have contributions from quark spin, gluon spin, and angular momenta. But previous data suggests that the gluon spin component of that is much larger than models would suggest. And from EIC data, this is just one example of something they could do by combining asymmetries such as this ALL, where the suffixes here are the helicity of the lepton, helicity of the proton, and plotting the output, then you can determine information about the polarized gluon PDF. So on this plot here, where we have, this is pseudo rapidity of the jet, then there's a difference between the projected result with polarized gluon and without the polarized gluon, and the difference is less than the statistical errors. And also here, although this variable transverse momentum of the jet is less constraining on the polarized gluon itself, the projected statistical error bands are less than the current PDF errors. And so it's another example of how that the new data there can hopefully help us to reduce the PDF uncertainties, which feed into all of our collider measurements going forward. From PDFs then to double parton scattering, which still connects the step from the protons to the hard scattering. This is another process which has now actually been seen at LHCb, and is something that we need to look out for. I would firmly place this in the category of things which were considered to be a small effect, but as we increase our collider energy will become more important. So what they did, just to explain this plot briefly, this is production of J psi, J psi as a function of their rapidity difference with various models. So the yellow line is purely double parton scattering. The other lines are single parton scattering in different models. And then they did a sort of linear fit of all of these to see what combination the data preferred. And it's not obvious from the plot because no one line does a very good job, but when that is performed, their conclusion was that it indicated a significant DPS contribution. And you can kind of see why that has to be from these large delta Y regions where the DPS contribution doesn't fade away as quickly as the SBS. A development a year ago here with double parton scattering is that there is now a new Monte Carlo implementation of it. So instead of, again, relying on inclusive theory predictions, one can actually do realistic experimental simulations, which includes a combination of SBS and DPS at the same time. And the most consistent way to actually measure the impact of the double parton scattering is to measure the difference. This is actually a toy model for SBS, but shows the differences in a few parts of phase space. And for a process at a fixed scale, if you then increase your collider energy to 100 TeV, say, then what that does is give you an increase in DPS relative to SBS, because it moves you to smaller values of X, where the protons tend to be are denser. So DPS is much more likely. Good. We're nearly finished. I'm not going to say too much about collective behavior because it's very far from my region of expertise, but I wanted to just include it at the end as an example of what I think was really quite an unexpected result from the LHC. And to be honest, one that we've still not completely understood, although I think it's beginning to be understood better and better. And the point here was that there are fluid dynamic, hydrodynamical models known to describe collective behavior within lead-lead collisions, but it turns out that that exact same models actually very well describe proton-lead and proton-proton collisions as well. And these are just examples of the so-called ridge effect illustrating that. And it's a nice note to end on here, because I think it's important as we look at the challenges ahead to remember that we can still be surprised by what we find. So I'll finish there just with my outlook, and really with the statement that I said at the beginning, that we still have a lot to learn from the LHC. There's at least 15 more datas and years of data, and a factor of 20 on the integrated luminosity. So when I look to future colliders, I'm in no way ruling out what is still to come at that excellent machine. And together with all the other program of experiments, either confirmed or possible in the future, then we have the opportunity to really deepen our understanding much more. But a theme throughout the talk has been that the current level of precision on the data is now so high that it's really pushing theory to the limit, and in many cases now exceeding it, but the theory community is responding, and we have time to respond further to the big challenges that will come from future colliders. So I'll end there. Thank you very much.
I believe that Gennaro is experiencing some further problem with the connection.
I was thinking that.
The others, can you hear us? So
yes.
Okay, grazie.
Yes.
Okay, I don't know. Of course, thanks a lot for this very nice and comprehensive presentation. And of course, the discussion is now open, and questions and comments are more than welcome. So,
I have a comment. If
yeah, sure.
Nobody. I'm Giancarlo. Hi, Jenny.
Hi.
Maybe a comment about, let's say, non-perturbative effect, because apart those encoded in Parton distribution function, because it's true that we are increasing the accuracy of fixed order and the sum calculation to impressive results, but sooner or later we have to face the problem that not all the QCD contribution are captured by factorization theorem. And so it seems that from that point of view, we have not so much improvement in the last let's say 20 years. And so my wondering is, what about NP, where NP is non-perturbative and not new physics? And can you comment on this or give us your impressions?
Yes, I can give you my opinion as a non-expert, which is that there when we're looking at MPI, low energy MPI underlying event, many of the models there are very reliant on the same models that they were a long time ago, and I think looking at some of those distributions, that's sort of what I had in mind when I was talking about differences between tools and Monte Carlo uncertainty. I didn't have more than that in my talk because I don't really have a clear answer on what prospect there is for improvement. I know that people are very keen to do it and are trying to think of ways to improve the models. It's possible that actually some of the collective behavior understanding will lead to improvements in the non-perturbative parts. But I have nothing more sort of concrete to say with that, unfortunately, at this moment.
Right. In the meanwhile, I think that Gennaro is back. Roberto, please.
Well, actually, I had a similar question than Carlos, because I mean, I'm taking inspiration from this last slide on the collective behavior, in fact. But the question, which I again understand, maybe Jenny, she said already, is not her prime expertise. Isn't lattice going to do anything about these non-perturbative effects, for instance, for hadronization? Isn't there any chance to compute fragmentation functions instead of PDFs, or it's something that from prime principles, you know, it's much harder, and there'll never be hope. Because in my experience, daily experience, these days, I find that yes, fragmentation functions are becoming a little bit of a problem in the future for certain studies. So now, I mean, I knew that Jean-Dong Ji was, you know, trying these PDF things already 10 years ago when I was at Maryland, but I didn't know that they now were so competitive. So now that you showed that, it came back to my mind that I mean, fragmentation function, maybe it's another direction where they could help if it's possible at all. I don't know if you have anything to say about this.
Yeah, all what I would say is that I believe that there are lattice efforts on fragmentation functions as well. I think, again, as a non-expert, but from what I've read and heard, they are trying. The sort of, there has been this huge PDF push recently, but I think they have the technology to improve on what's there already. I've also heard of efforts to improve the fitting of fragmentation functions in other ways using machine learning and neural networks, which hopefully might be able to shed some light. But other than a hope, as I say, I don't have a sort of concrete example of here's a calculation doing it right now with a result. But certainly, I hope in the next couple of years we will see new developments like that with new input, because it's so important.
Okay, thanks. At least you cannot report any reason why it's impossibly difficult to do that.
No, that might be my ignorance, but I don't know.
No, I mean, I have lunch with lattice people, because in Rome 3 there is a lattice group, and every now and then I get surprised by how they tell me that this is clearly impossible for some fundamental reasons that, to me, having a completely different expertise, I couldn't ever wonder. It was so hard. So yeah.
Well,
I think yes, we need some input from experts, but I'm glad that it's not obviously impossible.
No, and one should always be careful with the word impossible, even when somebody tells you it's impossible. You know, in 2012, they would have told you those PDFs were impossible, but it turned out they weren't. So it might be impossible now, but not.
Okay,
not
never say never.
Exactly.
Okay, I'll take the spirit. Thanks.
Hello, can you hear me now?
Yes.
Okay, sorry,
yes.
I have again some connection problem. So still on this slide, I don't know if you already discussed it. Can you explain why this comparison was done for alpha strong going to 0? Were they interested in checking the non-perturbative part in the infrared regime?
Yes, it's the caption there is actually slightly misleading. It's not just taking alpha S to 0. What they did was to check the leading the logarithmic behavior. They tuned the scales so that alpha S times log remained finite and equal with alpha S going to 0, which is how you test the logarithmic limit. But of course, yeah, I mean, they're not actually just applying to the non-perturbative regime. So it's a testing mechanism.
And is this discrepancy for, I mean, in the first two columns understood why, I mean, Pythia Dyer or beta equals 0 don't agree with the NLL?
Yes.
Are the authors working on improving pattern showers for this purpose, or is just an observation that, for example, for some observables, one should trust showers, and for others, maybe it's better if one uses a resound calculation, as long as this is it's exclusive enough to be interfaced to the detectors or something like that.
Yeah, exactly. I think it was more a point that the question of the logarithmic accuracy had not really been asked in this way before. And there were certain things which could be controlled, but when you got to your final, very complicated final state, actually, it was never even defined what the accuracy would be, never mind actually does it satisfy it. And of course, the definition was developed by the authors of the pan-scale approach. So they therefore, you know, they tested for the thing they had implemented, if you like, and found that it was there. But where we have issues perhaps with large uncertainties and systematic effects in the Monte Carlo, then I think it's something that these showers would not claim to have that accuracy, but when they so explicitly see it absent, then here I think it is I think they are working to see if they can improve it.
Okay, thank you.